Hello, and welcome to our proof of the generalized Cauchy integral formula. We'll start with a function f that's holomorphic on the open set D. D here does not have to be a domain or a star domain, just open. If this is the case, then f is also analytic on D. So what does this mean? If you have a point z0 in D and a number r greater than 0, such that the closed ball centered at z0 of radius r is contained in D, then you can write f of z as the power series sum from k equals 0 to infinity of ak times z minus z0 raised to the power k for any point z in the ball centered at z0 of radius r, specifically the open ball centered at z0 of radius r. And the coefficients are given by the following formula. Each ak is 1 divided by 2 pi I times the integral over the circle xc minus z0 equals r of f of xc divided by xc minus z0 raised to the power k plus 1. And this, of course, is equal to the kth derivative of f evaluated at z0 divided by k factorial. So here is the remarkable thing about the generalized Cauchy integral formula. If f is holomorphic, being once differentiable, then f is in fact infinitely differentiable, and not just infinitely differentiable, but we can also write f as a power series. And on what open set or ball does that power series converge? It converges on the largest ball centered at z0 of radius r, such that the closed version of that ball fits inside D. So this tells us a great deal of information about f, about its derivatives, and about its power series expression. Now, to prove the generalized Cauchy integral formula, we will largely rely on the original Cauchy integral formula and also the geometric series. So let me remind you what the geometric series is. If you have a point w in the complex plane with the modulus of w less than 1, then the following is true. 1 divided by 1 minus w is equal to the sum from k equals 0 to infinity of w to the k. So this sum of powers of w converges, and it converges to the nice, neat expression 1 divided by 1 minus w. So with this in mind, let's prove the generalized Cauchy integral formula. We'll start with the regular Cauchy integral formula, which tells us that f of z is equal to 1 over 2 pi I times the integral over xc minus z0 equals r of f of xc divided by xc minus z. And here z is a point inside this circle centered at z0 of radius r, with the whole ball being contained in our original set D. Look at the integrand. It's f of xc divided by xc minus z. We're going to rewrite the 1 over xc minus z part as follows. 1 over xc minus z is 1 divided by xc minus z0 plus z0 minus z. So I've added and subtracted z0. And that I can group together as 1 over xc minus z0 minus the quantity z minus z0. And then I can factor this. I'll pull out a factor of xc minus z0. So I get 1 over xc minus z0 times the quantity 1 minus z minus z0 divided by xc minus z0. Hit pause for a moment if you need to chase through all the algebra here. This is important technical stuff. Okay? Now, why can we do this? I'm allowed to divide by xc minus z0 here. Is that okay? Well, yes, because xc is my variable of integration, and I'm assuming that xc lies on the circle centered at z0 of radius r. That is, the modulus of xc minus z0 is r, which is positive, so xc minus z0 is definitely not 0. At the same time, I'm also taking z inside the ball of radius r centered at z0. So what does that mean? The modulus of z minus z0 is less than r. And then this tells me that the modulus of the fraction z minus z0 divided by xc minus z0, The modulus of the fraction is just the modulus of the numerator divided by the modulus of the denominator. Now, what's the modulus of the denominator? Modulus of c minus c0 is r. And how about this numerator modulus of z minus c0? Well, that numerator is less than r. So the modulus of the quotient is ultimately strictly less than r divided by r, which is equal to 1. Now look at that factor in the denominator up there. I have a 1 minus z minus c0 divided by c minus c0. And the modulus of z minus c0 divided by c minus c0 is strictly less than 1. I'm going to expand that factor as a geometric series. So 1 divided by 1 minus z minus c0 over c minus c0 is really going to be the sum from k equals 0 to infinity of z minus c0 divided by c minus c0, whole thing raised to the power k. Now, let's look at the whole integrand from the Cauchy integral formula. I had f of c divided by c minus z, and that I rewrote as f of c divided by c minus c0 times 1 minus z minus c0 over c minus c0. And that I can factor just a little as f of c divided by c minus c0 times the big fraction 1 divided by 1 minus z minus c0 divided by c minus c0. Now that big factor on the right, I know that's going to be the geometric series. So this is f of c divided by c minus c0 times the sum from k equals 0 to infinity of z minus c0 divided by c minus c0 raised to the power k. And let's put everything together. I'll multiply through the sum. This will be f of c times z minus c0 raised to the power k. And then on the denominator, I had a c minus c0 times a c minus c0 to the k. So that gives me a c minus c0 to the k plus 1. Again, hit pause and make sure you can chase through all the algebra. So going on, now we'll look at the integral. I'm going to multiply both sides of the Cauchy integral formula by 2 pi I, just so I don't have to keep rewriting 2 pi I on the slides here. So I have 2 pi I times f of z is from the Cauchy integral formula, the integral over the circle c minus c0 equals r of f of c divided by c minus z. And this is now the integral over that same circle, c minus c0 equals r, of the sum from k equals 0 to infinity of f of c times z minus c0 to the k over c minus c0 to the k plus 1 from all the geometric series work I've done. So everything here is a totally legitimate equality, either from the Cauchy integral formula or from the geometric series. Now I'm going to do something a little dicey. I'm going to interchange the sum and the integral. We know a couple of things about interchanging sums and integrals. If this were a finite sum from k equals 0 to 5 or 20 or 50, I could interchange the sum and the integral. If this were a sum over a power series in c, I could interchange the sum and the integral. But here's the thing. The integral is taken with respect to the variable c, not z, and here c is in the denominator. So this integrand is not really a power series, but nonetheless, some more technical theory on interchanging sums and integrals and uniform convergence allow me to do this. We are simply going to accept this as true. So I get 2 pi I times f of z is going to be the sum from k equals 0 to infinity of z minus c0 raised to the power k. So z minus c0 doesn't depend on c, I pulled that out, times the integral over the circle c minus c0 equals r of f of c divided by c minus c0 raised to the power k plus 1. So the sum and the integral switch places, and everything that had a c in it stayed inside the integral, just this factor of z minus c0 to the k. But look what I have now in this sum. I have a sum of powers of z minus c0 times an integral. This integral no longer depends on z. This integral is a constant in z. And so if I just divide by 2 pi I get f of z is the sum from k equals 0 to infinity of the single complex number 1 divided by 2 plus 2 pi I, integral c minus c0 equals r, f of c divided by c minus c0 to the k plus 1. That is one complex number that depends on k and z0, but not z, times z minus c0 to the power k. This is a power series in the variable z, centered at z0, with a lengthy but explicit k-dependent constant in front of the z minus c0 to the k. This is the power series expansion for f.